All right, welcome to 1-4 notes on one-sided limits and a little bit more with continuity. So before we start, we're just going to list a few properties of continuity. Again, these are properties that you probably wouldn't really think twice about, but we do have to say them just to say that they're true. So if we have two functions, f and g, that are continuous at x equals c, then the following functions are also continuous at c. Scalar multiple, so I guess we should say that b is any real number. You have b, so a number times a function f. If f is continuous, then that means this is also continuous. If you add or subtract two continuous functions, that resulting function is also continuous. The product of two continuous functions is also continuous. The quotient of two continuous functions is also continuous, provided that the function in the bottom is not zero. And then if you compose, I guess that's not really the right word, a composite function, f of g. So I don't know if you've seen this notation before. F, and then it's like a little O, and then G, that's the same thing as F of G of X. That is not beautiful writing, but it will do. Okay. So let's talk about one-sided limits. The good news is that we've already talked about this a lot, so this should be kind of familiar to you. A limit, as we know, can be evaluated from just one side of a point C. Let's erase that off up there. These are called the right-hand and left-hand limits. The right-hand limit evaluates the limit as a function approaches point C from values that are greater than C. Right here, this is the notation. X approaches C from the right of f of x. The left-hand limit evaluates the limit as the function approaches the point C from values less than C. X approaches C from the left of f of x. Note, and we have talked about this already too, one-sided limits can occur where normal limits do not. So here's an example of that. All right, so we're going to evaluate the following. So first one, the limit as x approaches 3 from the left. So as our x values get closer and closer to 3, the corresponding y values are getting closer and closer to 1 from the left of 3. So that is why we have 1 right here. B, the limit as x approaches 3 from the right. So as our x values over here get closer and closer to 3 from the right of 3, our function is up here, and the corresponding y values are getting closer and closer to 4. So the limit as x approaches 3 from the right is 4. Now, since these are two different values from the left and the right, that's one of our 3 ways that the limit does not exist. Therefore, the limit as x approaches 3, just in general, of f of x does not exist because the limits from the left and from the right are approaching 2 different values. So f of 3, which is just what is the function value at x equals 3, is 1. So if we're looking here, it's not defined up here, it's defined down here. So it is 1. All right, so that's from a graph, which we have done. What we haven't really done is evaluating left and right-hand limits just using substitution. So the good news is it's kind of the same idea as what we were doing before. So if we have here, we have the limit as x approaches 2 from the left of 3x over x plus 4. So the first thing we want to do is just plug in 2. And you can see that when we do that here, we get 6 over 6, which is 1. So that means that the limit exists at 2. So since the limit exists at 2, that means the left limit also has to be the same thing. So the left and right limit both have to be 1 in order for this limit to exist. So that means all we have to do is plug in 2 here, and we find the left limit. Same idea, so this is x approaches 3 from the right. Now we didn't say this, but if we were to just plug 3 in here, we would get 0 over 0, which tells us that's the indeterminate form. That tells us that we need to try something else. So hopefully it's obvious to you that we should factor here. So in the numerator, we have x minus 3, and then in the denominator, it's x minus 3 times x plus 3, a difference of squares. So we can cancel out the x minus 3 factor here. And then we're left with 1 over x plus 3. We just plug in 3 here, and we get 1 over 6. So that only works if when you do your direct substitution, if you get a real number, like we got 1 over here, we got 1 over 6 over here, that's just your limit, whether it's left or right, or just a regular limit. So we are going to run into a little trouble with this one, because when we plug in 0, we get -1 over 0, which we know is a vertical asymptote. But since it's a left or right limit, we can be more specific than saying it doesn't exist. So we're going to say that it's -infinity. Now, how do we know that it's -infinity? Well, there are a few ways you can think about this. We're going to think about it numerically. So if you were to plug in numbers that were getting really, really close to 0 from the right side, so that means they're positive, but really close to 0, I'm just going to choose, let's just choose 0.01 minus 1 over 0.01 squared. So I'm just plugging in a number that's really close to 0 on the right side of it, so a positive number really close to 0. And I just want to know if this is going to be positive or negative. And just looking at this, I don't even need to figure out what it is. I know that this is going to be a negative number. So that means if we keep doing this, if we got even closer to 0 from the right, we would still get negative numbers. And we know it's an asymptote already, so that means we know it has to be -infinity. So just using some number sense there to be more specific about this limit. All right, next page. So the existence of a limit, we've kind of talked about what happens when a limit doesn't exist. There were 3 ways. It was in the first section. It's when the left and right don't equal each other, when it's unbounded, or when it's oscillating. So this shouldn't seem too shocking to you. So if f is a function and c and capital L are real numbers, the limit of f of x as x approaches c is equal to capital L if and only if the left and the right limit both equal L. So they equal each other and they equal the same number, which is L. So that probably shouldn't seem too shocking because we have talked about that. But now we've said it, so it's got to be true. All right. So we can use this idea to extend the definition of continuity on an open interval to a definition of continuity on a closed interval. So now instead of looking at the whole -infinity to infinity, we're just looking at a specific interval on a graph. So a function is continuous on the closed interval a to b if, first of all, it has to be continuous on the open interval. And then the limit as x approaches a from the right of a has to equal the endpoint f of a. So let's see if we can draw this. So as we get closer and closer to a from the right, that's not a straight line, but it'll do, the y values. Okay, I had to pause because Mr. Tebow was making an announcement. So what I was saying, as the x values get closer and closer to a from the right, the corresponding y values should be getting closer and closer to what the actual value of f of a is, whatever that may be. Likewise, number 3 here, the limit as x approaches b from the left has to equal the actual endpoint. So as we get closer and closer to b from the left, oh, that's not great. The corresponding y values have to get closer and closer to what the actual value of f of b is. So three things: the function has to be continuous inside the interval, so on the open interval, not including the endpoints. And then the right limit as x approaches a has to equal the endpoint f of a, and the limit as x approaches b from the left has to equal the endpoint f of b. So that's continuity on a closed interval. All right, one last thing here. Making piecewise functions continuous. So for a piecewise function to be continuous, each function must be continuous on its specified interval, and the limit of the endpoints of each interval must be equal. Okay, so that's kind of saying a lot. So let's just look at this first example here. What value of k will make the given piecewise function f of x continuous? Okay, so first of all, f of x equals sine of 2x when x is less than or equal to pi. So first I'm going to ask myself if this is continuous. And it is. Sine of 2x is continuous everywhere, so that's not a problem. Now I'm going to look at 2x plus k when x is greater than pi. So I'm looking at that. That's just a line, so that's definitely continuous. So I don't have any issues there. So now what I want to do is choose a k value that would make these two things the same at x equals pi. So what we're really saying is we want the left-hand limit as x approaches pi from the left of f of x. That's going to be given by sine of 2 pi, since sine of 2x is the function that is to the left of pi according to the piecewise function. And the limit as x approaches pi from the right of f of x is going to be given by this line here, 2x plus k, since that's defined as being to the right of pi. And what we want is we want these to equal each other, because if these two limits equal each other, then that will make the function continuous. So we set the left-hand limit, so sine of 2 pi equal, well, it's 2x, and we're plugging in pi because that's the point that we're concerned with. So sine of 2 pi equals 2x plus k, 2 pi plus k, and then we just need to solve for k. So sine of 2 pi is 0 equals 2 pi plus k, which means k equals negative 2 pi. So that's the value of k that will make this piecewise function continuous. All right, moving down to the last example. Again, for what value of k is the function f of x equals all that continuous at x equals negative 3. So this is piecewise. It's defined by this rational function everywhere except for when x equals negative 3. And then this function is equal to k at x equals negative 3. So this is just a point, k, x, and k. The whole function is going to look like whatever this is, except for at this one point. So what we want, this will have a hole in it at negative 3. So we basically want to fill that hole in with x and k here. So again, to be continuous, we want the left and the right limits to equal each other. And like I said, we're going to have a problem here because this is going to be a hole. So there's a hole at k. So what we're going to do is we'll factor this. The numerator factors to 2x minus 1 times x plus 3. The denominator is x minus 3, x plus 3. And then we will plug in x equals negative 3 to our resulting 2x minus 1 over x minus 3, and we get 7 over 6. So if we were to, that's where the hole occurs. So if we were to fill that in and say that k is equal to 7 over 6, then this function will be continuous. And that's all on that. Hopefully most of that made sense.